Hey, Algebra. So in the past, we've been looking at functions, different types of functions, domain and range. Well, today, in this video, we're going to be talking about properties of functions. And the three things that we're going to cover are whether a function's even or odd, if it has local maximas and minimums, and the average rate of change between 2 points of a function. All right, so let's get started. So first, let's talk about even and odd functions. Well, what is an even function? An even function is if you can plug negative x into our original function, just f of x, we can show that f of x is equal to f of negative x. So that's what an even function is. And what it looks like graphically is it's symmetric about the y-axis. So if you were to put a mirror on the y-axis, it would mirror one side. So here's our right side, and it's being mirrored on the left. Okay, so that's an even function in a nutshell. Well, what's an odd function? An odd function, so you're doing the same thing. You're plugging this negative x into f of x. But instead of getting f of x is equal to f of negative x, you want to get that f of x is equal to the negative f of x, or the opposite. So that's the big difference. Okay. Graphically, what is it going to look like? Well, graphically, it's going to be symmetric about the origin. And what the heck does that mean? So symmetric about the origin, think about it like this. If you have anything in quadrant 3, rotate it 180 degrees so that everything's into quadrant 2, or I'm sorry, this is quadrant 4 into quadrant 2. So you flip it 180 degrees, and you should get the same thing. So we flip this, got 180 degrees, we should get it to look like that. And it doesn't matter which quadrant, it's like flipping 180 degrees. Another thing to look at here with symmetric about the origin is you have some point x comma y, which is a point on your graph. If it's symmetric about the origin, if it was flipped 180 degrees, you just get a new point that's negative x, negative y. Okay, so that's symmetric about the origin. Now let's go through some examples where we show whether a function's even or odd. Okay, so here, just laying down the foundations of how to show something to be even or odd. You just plug that negative x into f of x, and if it equals f of x, the original function, it's even. If it equals negative f of x, it's odd. Okay. Here's our example. So what do we do first? First thing we do, put in that negative x to f of x. So when we do that, we'll get that it's equal to negative x cubed plus 2 times negative x. Okay, so we know that anything cubed or anything negative that's cubed will stay negative. So we can write this as negative x cubed minus 2x. We just move that negative in front of that 2. All right, and so that's it. So what have we just shown? Well, if our f of x is equal to our original function, x cubed plus 2x, well, we know that that doesn't equal this. So this doesn't equal f of negative x. And so we've just shown that it's not even, since f of negative x doesn't equal f of x. Could it be odd, though? So what's negative f of x? Well, that's just going to be equal to negative x cubed minus 2x, because we're just multiplying everything by negative 1. Well, that's equal to this right here. So we get that this is equal to f of negative x. And so what we've just shown is that f of x is odd. Okay, now let's look at it graphically. So here you can see it's oriented about the origin, in that if you flipped it 180 degrees, it'd look like the exact same thing. So therefore, f of x is odd. Now let's look at these examples. So how do we show that x to the fourth plus 1 is an odd or even function? All right, so first thing we do, what is f of negative x? So we throw in a negative x for every x. Okay, so we know that any negative to an even power ends up being a positive. So we can say f of negative x is just equal to x to the fourth plus 1. Well, we can see that this is equal to our original function. So this is just equal to f of x. So we look at our even rule. We're saying that this is equal to f of negative x. We have just shown that this is even. So if we draw a graph of this, it's just going to look like a skinny parabola, the y-intercept 1. We can see from this unperfect picture that it's symmetric about the y-axis. And so since it's symmetric about the y-axis, we can say that it's even. All right, this last one though. How do we show it's even or odd? Plug in that negative x. Okay, so now let's simplify it. Any negative to an even power is always positive. Okay. Well, we can see that this does not equal our original function, so we can say that this does not equal f of x. Therefore, it's not even. Well, then, what is negative f of x equal? And this is just equal to everything times the negative 1. So we'll have negative x squared plus x minus 1. All right, but is that equal to our f of negative x? And the answer is no. So we don't have that negative right here, and this is a positive. So, therefore, this is not equal to negative f of x. So it's not even, and it's not odd, so what is it? And it must be neither. So if you show that a function's either odd or even, it's just neither. All right, now let's look at it graphically. And we could see that's not reflective about the y-axis, and that it's not reflective about the origin, because if we flipped it 180 degrees, we wouldn't get the other side. So you can clearly see from this graph that is not even or odd. All right. So now that we've gone over even and odd, let's talk about our second properties or function. And so let's talk about increasing or decreasing slopes. And so a function is increasing when the slope is positive. So here, a function's increasing when we have a positive slope. And when we have our functions decreasing, its slope is always negative. So where is our slope, or where is our function increasing? So a function has a positive slope all the way up to here, all the way up to negative 2 comma 9. But after that, it starts to go down. And so we'll have it have a positive slope again here, and another positive slope right here, all the way out to infinity. Now where is it decreasing? So here, all the way out from infinity, or negative infinity, it's decreasing. And we have a negative slope right here. So therefore, it's decreasing. And a negative slope here. So therefore, that's decreasing. So that's all the places where our function's decreasing and increasing. But now let's talk about local maximas and minimums. And local maximas are going to be on a hill like this, where the left side of the hill is positive, and the right side is a negative slope. And a local min is the exact opposite. It's like a bottom of valley. It's going to have a negative slope on the left and a positive slope on the right. And right here will be our local min, and right here will be our local max. So what's our local maximus for this graph? So right here, -2, 9, it's on top of the hill, so it's a local maxima. So we can write -2, 9. And it's also a local maxima right here. It's just 3, 4. Now, some of you guys might be thinking, well, isn't infinity the biggest point? So shouldn't that be the maximum? And the answer to that is, yes, it's the maxima, but it's not the local maxima. The local maxima is just when we look at a finite graph and we look for all the points that are on top of the hill. And the same thing goes for local minimum. I have a local minimum right here, here, and here. This would be -8, 9, 1, 0, and 5, 0. All right, so the last thing we had to discuss in this video is the average rate of change. So what is this average rate of change? Also known as the AROC, AROC. This is the slope of the secant line between our point x, f of x and c, f of c. And we can look at this first point right here as x1, y1, and this one as x2, y2. But what is the secant line? We haven't seen this before. What is it? Well, the secant line is this line right here that connects to both our point x, f of x and our point c, f of c. And that's our secant line. And the slope of the secant line represents the average rate of change between those 2 points. So we can also write slope of secant line. Is equal to this also. So yeah, the average rate of change represents the average amount of change between 2 points. That's what it means. But you can think of it as the slope of the secant line. Okay, so let's look at some examples where we find the average rate of change in a function. So here, we're going to find the average rate of change of h of x. And we're going to find that average rate of change from the points x is equal to -2 and y is equal to 6. Okay, but we need to put it into this formula right here. So what's f of -2? So that's where we substitute negative in. And for all of our x's, oops, shouldn't be an x right there. And so this is just going to be equal to 11. All right. So that's our f of -2, or f of x. All right, so now we have to solve for f of 6. And that's where we're just going to throw 6 into all of our x's. So this will equal okay. I just add everything up. When we do, we'll end up getting this to be 27. All right, and so this is equal to f of -6, or our f of c. All right, now that we have f of x and f of c, let's go ahead and plug everything in to our average rate of change. So our average rate of change, or AROC, is equal to f of x, which is f minus 2, or 11, minus our f of c, which is 27, all over x minus c, where our x was -2, minus 6, which is our c, or our y up here. Okay, so now, just like solving our slope, this is just going to be equal to -16 over -8. Oh, nope. I'm sorry. That's right. So this will be equal to 2. And so 2 is equal to our average rate of change between our points -2 and 6. This is equal to our average rate of change. Now what if we look at this graphically? And here's our graph right here. So when we look at x is equal to -2, if I put a dot right there, and we look at x is equal to 6, 1, 2, 3, 4, 5, 6, it's something way up here. When we draw a secant line between those 2 points, we should get the slope of that secant line is equal to 2. It's just another way to look at it. All right, so let's do one more example. We're going to use this, we're going to look at the same function here, but this time I want you guys to pause the video and come up with the average rate of change between 2 and 3 on your own. All right, so this is what I ended up getting. And so to solve for f of x, I put 2, and for x, I got f of x is equal to 3, and to solve for f of c, I ended up putting 3 in for all my x's, and got f of c is equal to 6. Now at the average rate of change, I plugged in my f of x, my f of c down here, and solved that way. And I ended up getting my slope to be 3. Now how can we show this graphically? Well, we go over to 2 on the x-axis, we go over to 3, go up to where the output is, and draw a line connecting those 2 dots. And so we should get a line with a slope that's equal to 3. And so it's just another way to check your solutions. Below this video, there'll be a link for you guys to click on. That'll take you to Google Docs, and there'll be your questions for you guys to answer there. So thank you for watching, and I hope this went well for you.